right, thank you. Yes, I'll explain some results about derandomizing local distributed algorithms, and this is a joint work with David and Fabian, who are both sitting there. So let me recap on what's the setting. This is something that Nati Lineal defined some 30 years ago, more than 30 years ago at Fox. So it tries to capture the locality issue in distributed systems and computer networks. So we're going to think about something very abstract and mathematical. It says, let's say this is the computer network. It has a communication network, right? Let's abstract it as a graph with some n vertices, one processor on each of the vertices of the graph. So these are the computers of the computer network. And they can communicate with each other, let's say, in synchronous rounds. So let's clean up the setting, and it's a synchronous round model. Per round, each node of the network gets to send messages to its neighbors, receives the messages that the neighbors send to it, does some computation, and then the next round, and so on. And in the most basic version of the model, we do not assume any bound on the message sizes or the computational power of the nodes. Even on this seemingly very powerful model, there are many questions that we still don't understand. This talk is about this abstract model. The usual setting is that when we talk about a graph problem, let's think about, let's say, a coloring problem. Initially, the computers do not know the topology of the graph. They just wake up to the system, basically. And at the end of the computation, they should know their own part of the output. Let's say the color of the node and the coloring of the graph, right? So this would allow you to do some scheduling of the tasks in a computer network or things like this, right? So that's the setting that the model talks about. And the most important measure in this model is time complexity, or the round complexity, the number of rounds that it takes so that all the computers are done with their computation. And well, as the model name suggests, local, the whole model is about locality of, let's say, graph problems in the following sense. If somebody gives me an algorithm that runs in, let's say, t rounds for some graph problem, what that person is really telling me is that there's a function mapping the topology of the t-hop neighborhood to the output, right? Because what can you learn in t-hops, in t-rounds? In one round, all that you can learn, the most that you can learn is, the topology within your one-hop neighborhood, 2 rounds, 2-hop neighborhood, and so on. So basically, it's a mapping from local areas to the output. So the area is really trying to understand the locality of graph problems. Now let's say, here's a very simplified summary of the state of the art in this area. There has been 30 years of research in the area, so this is really simplifying it. But to some extent, this is explaining what we know about the area. If you talk about randomized algorithms, typically we have, let's say, log n round algorithms, or in cases even faster than log n round algorithms, let's say for coloring or MIS. While if you ask about deterministic algorithms, we are far, far away from that. Polylog n would be really nice to have. The best that we know is typically 2 to the square root of log n. Okay? So this is much higher than polylog n, but it's also below any polynomial, right? And well, this actually brings us to probably the most well-known open question of the area. Nati Lineal in his first paper already asked, can we solve MIS in polylog n time deterministically, right? At the time, there was a well-known log n round algorithm by Luby and Alon, Babai, and Itai, which solves the MIS problem, maximal independence set problem randomized in log n time. To this day, we still don't know a polylog n time deterministic algorithm. And actually, there are books on this area. If you open the books of the area, for instance, there's one of them relatively recently written. This is by Barenboim and Elkin. There's a last chapter that talks about the open problems. If you open the open problems and go through them, the first 5 of them are basically asking, well, how about this problem? Can we solve this one deterministically? How about that one? Can we solve this one deterministically? And so on. So now you might ask, well, why do you guys care about deterministic so much, right? There's a part of it which is kind of the standard reasons. One is that it's a fundamental question to understand the power of randomness, typical of many settings. Something that is a bit more important in distributed systems is that deterministic algorithms are much more preferred because typically things are composed with each other, and when you have a deterministic process, it's much easier to take care of the issues like faults and so on. But there's a reason that actually brought me to this area. This is the reason that I actually started going into this problem. This is a much more modern reason, and I think it's very unique to kind of the setting of distributed computation, which is the following. If you want a faster randomized algorithm, we provably know that you have to come up with a faster deterministic algorithm. Okay? So this might sound a bit mysterious. Let me say a little bit about how this goes. Let me pick 4 of the central problems of the area. These are the problems that have been studied since the 80s. This kind of shows the state of the art about these 4 problems. I'm not going to dig into what the problems really are. The arrows also show the reductions that we know among these problems. But the thing that I want you to observe is the following. So I'm plotting I'm sort of showing the randomized complexities on the right side and the deterministic complexities on the left side. If you focus on these, you see that there is a dependency on n, the size of network term, on the randomized side. Actually, these are just copies of the complexities on the deterministic side, where you replace n with a log n. Okay. If you're familiar with LLL type of settings, lowest local lemma type of settings, these are just because of the shattering technique, which do something to the graph, break it into small components, and then these small components, roughly log n size, you can solve them using the deterministic algorithm. So that's roughly the one direction, which is how do we know, how do we solve these randomized problems and get these complexities? There's a converse to it, which is, in my opinion, much more surprising. The proof is not that hard, but it's much more surprising to see it, is that we know that for these problems, and in fact for any locally checkable problem, okay, I will get to that in a second. For any locally checkable problem, the randomized complexity for graphs of size n is at least the deterministic complexity on graphs of size square root of log n. Okay. Now, if you look at those bounds and just replace, let's say, n on the deterministic side with a log n, you basically come back to the randomized side. Saying it differently, if you somehow manage to magically come up with a better deterministic algorithm, a better randomized algorithm, better than these bounds, we can extract out of that a faster deterministic algorithm. Okay? In a sense, it says that if you want to improve these bounds, you might as well just go and directly attack the deterministic problems. So this is kind of one reason that is a bit different to the local model, and this is the reason that we care about deterministic algorithms. So let me explain a little bit about our results. So we have 2 general results about de-randomization, about things that we can solve, we can de-randomize in the local model. One result says the following. If you give me any algorithm for any locally checkable problem, now I have to specify locally checkable. I mean problems where the constraints of the problem are local or span a constant neighborhood, let's say. Okay? For instance, coloring. Coloring, the constraints are really about each node and its neighbors, right? Things like this. So imagine generalizations of this. I'm not going to go into formalizing this. Any locally checkable problem, anything that the solution can be checked within constant rounds deterministically in this model. For any of those, if you give me an R-round algorithm, we can de-randomize it and get a deterministic algorithm which runs in R times 2 to the square root of log n. Okay. So in terms of the 4 classic problems that I was showing on the picture, this doesn't really say anything new. But in terms of many other problems, this is much better than anything that we knew before. I mean, we didn't have any general de-randomization result. There's a second result which says the following. If you give me an R-round randomized algorithm, I'll get a deterministic algorithm which runs in delta to the order of R. Delta here is the maximum degree, so exponential in the round complexity of the randomized case, plus some, let's say, less significant term, R times log star n. Okay? So now a few comments about these bounds. One is that this 2 to the square root of log n overhead, it's not ideal. I would like to conjecture that this should be polylog n, but we are nowhere close to that. And any improvement on this 2 to the square root of log n, this would be a major breakthrough in distributed computing. I mean, this would be resolving 25 years old open problems. On the second theorem, we know that this exponential blow-up is in some sense the best possible if you talk about general results in the following sense. We know there are problems. For instance, there's this one problem, sinkless orientation, where the randomized complexity is log n and the deterministic complexity is log n, and the upper and lower bounds are these values. Okay, so it's tight. So there's an exponential blow up necessarily for any derandomization process. Out of these derandomization results, we get some results for some other problems that we care about. There are basically two directions, two general problems that they might sound a bit unnatural, but using those unnatural problems, we can solve many other natural problems. So let me talk about these things. One is the problem of computing a maximal matching in a hypergraph. By maximal, I just mean something that you cannot add any more edge to it. Okay. And in hypergraphs of rank R, I mean every hyperedge has at most R vertices. Okay. So we get an algorithm using the second derandomization result and a few other ideas, which runs in poly of R times log n. This actually improves on a result that last year we had at Fox. That one didn't have a good dependency on the rank. And you can use this general result on hypergraph maximal matching to solve many of the more natural graph problems. Okay, so I'm not going to explain these connections. These are known from, let's say, our result from last year. For instance, 2 delta minus 1 edge coloring, or orientation of the graph with best, sort of roughly speaking, the best maximum out degree, or 1 minus epsilon approximation of maximum matching. These are all things that we can reduce to hypergraph maximal matching, and by this theorem 3, we can get better algorithms for them. For instance, those two corollaries are, they resolve these open problems 3 and 10 in the book. I should say that the open problem 3 was actually resolved because of the result last year, but what we get now is much simpler and also much faster. Anyway, so there's a second direction of general results that we get out of this randomization. This one has to do with the lowest local lemma. I should briefly recap what lowest local lemma is. So I'm going to be talking about the simple case, the symmetric case, and the variable setting of it. So we'll have a set of variables, and we have a number of events defined on these variables. And we assume that each of these events has some probability at most p to happen, okay, based on a random assignment of the variables. And also there are some dependencies between the variables in the sense that you put a graph between the events. You connect every two of them if there are variables that are shared between them. And we'll assume, or we'll use d to denote the maximum degree of this graph. So the famous result of Lowas says that if e, the base of the natural log, times p times d is less than 1, roughly saying that if a local union bound is satisfied, there's an assignment to the values that avoids all the bad events. Now, this thing turns out to be also very important for this area of local. The coincidence of the names having local in it is actually not a coincidence. There are strong reasons behind them. There was a really nice result, again, last year at Fox by Chang and Petty, which says the following thing. For any problem, any, let's say, locally checkable problem, and let's focus on graphs of constant degree, if you give me an algorithm that runs in little o of log n, so faster than log n rounds, I can automatically speed this algorithm and make it run in the time complexity of solving LLL, okay, in graphs of size n. What do I mean by time complexity of LLL? I really mean even a more relaxed version of LLL where p times some power of d is less than 1, some constant power of d is less than 1, and graphs of constant degree. Okay, so you can speed up things that are running in log n or in little o of log n to the complexity of lowest local lemma. In a sense, lowest local lemma is a complete problem for sublogarithmic regime. Now, what do we know about this TLLL? So, well, Chang and Petty, they're very brave. They conjectured that this should be log n. Okay, what did we know at the time? Something follows from the result of Moser and Tardosh that gives a log squared bound. There was an improvement to log n a few years later. There was also a lower bound about a year before that, which says that we cannot go below log n. Okay? So, at the time, the results seemed like you can speed up anything that runs in little o of log n to something that runs in o of log n. So, well, shortly after we said that, we showed that, there is a speed up. the LLL complexity, we showed that it's at most 2 to the square root of log n. Okay, so this is something that is below any log n or any power of log n, but also much above any power of log n. So somewhere in between the two bounds. Now, out of the results of this paper, we get some improvements. It's not the last word on the problem, most likely. What we get is the following. The bound is 2 to the 2 to the, some power of 2's. Now, the exponent is square root of log, log, log. The point is that there is one more log in the exponent than the base. So this is, just even I equals to 2 is much faster, much more than polynomially faster than the previous bound, but you can set I much larger and you get better and better bounds. I'm not going to dig into it too much of what this really means. Let me say what's the connection to, why is this a result of de-randomization? Because I'm talking about randomized algorithms. It has to do with the connection that I mentioned at the beginning. So what we really get is, we get some deterministic algorithm for this problem. I'm writing the bounds there, 2 to the 2 to the, with some log of the degree and then square root of log log, but not with one additional log, so just with the same number of logs. So this is a deterministic result, and we get also a randomized result. Basically, these things are working, you get a faster deterministic algorithm, you feed it to the procedure, you get a faster randomized, then you de-randomize it, and so on and so forth. So that might explain the mysterious look of the bound that we have. All right, so I will not get time to talk about how these things are derived, but I think there is one basic idea in the paper that, majority of us should know. This is, it surprised us that this thing is so powerful. So I'm gonna, run through this idea. It's extremely simple, so hopefully everyone will be able to follow. The idea is to prove this result of, you give me an R-round randomized algorithm, I want to turn it to a deterministic algorithm that runs roughly in delta to the R, maximum degree to the order of R. So this will be in 2 steps. One is that I'll take this randomized algorithm and I'll kind of de-randomize it to something that also has locality R, but this second one will not be a distributed algorithm. It's going to be a sequential thing. I'll explain in a second what I mean by a sequential thing. And then there's a second step of turning this sequential thing back to a distributed one, and there is the place that we get this blow-off of delta to the order of R. So let's see the first step. Well, basically it has to do with understanding what this randomness is used for in the distributed computation. So let's say I want to fix the randomness of the vertices of the nodes, right? And I will do it sequentially, so I'm not so worried about rounds right now, okay? So I'll go over an order of the vertices, an arbitrary order of the vertices, and try to decide about their randomness. I'll pick one vertex, V, and it has some randomness, right? It's using some randomness, and I want to get rid of this randomness. Well, we'll throw our basic tool at this, which is, conditional expectation. The randomness of this node only impacts its R-hop neighborhood, because we are talking about R-round algorithms. So you'll just try to fix this randomness in a way that the expected number of violated constraints does not grow. Okay? So you fix that randomness, you go to the next node, you read its R-hop neighborhood, you fix the randomness, and so on. Right? So this is now a sequential process. Hopefully it's clear what I mean by this. Now let's turn it back to a local process or a distributed process. For that, this is one of the basic tools of the area. We'll take a coloring of the graph. The coloring should be such that any 2 vertices of the same color have distance at least order of R from each other. So let's say this is my coloring. Let's say that the red vertices are more than R hops apart. And I'll use this color as a schedule to run my sequential process, okay? What do I mean? Let's say I'll pick the vertices of the first color, and I'll do the same de-randomization idea that I had before on these guys. Since they are far apart, their de-randomization processes will not impact each other. Each of them can read its own neighborhood, fix its randomness as it wants. I go to the next color, fix their randomness, next color, fix their randomness. G to the R, the graph where you put edges between vertices of distance R. This thing has degree at most delta to the R, so you can color it. Using known techniques, you can color it with these number of colors, and that gives a very basic de-randomization idea. This is extremely simple, but it turns out to be very powerful it led to some of the results that I explained. Let me summarize. So we get two general de-randomization results. One has this overhead of 2 to the square root of log n, and one has this exponential blow-up. And we also got some results for hypergraph maximal matching and lowest local lemma. Let me say a little bit about open problems. So of course, improving any of these bounds, that's an open problem, right? In some cases, we have some kind of a tightness understanding, but we don't really know that these bounds are tight. Any of them, especially in the first two cases, improving them would be very significant. Let me say two problems that I feel are much more within reach. These are concrete things that I think should be within reach, and they would have significant consequences. One is, in the case of this hypergraph matching, hypergraph maximal matching, right now we have a dependency of R squared. It would be great to get something that has a dependency just sublinear in R. Okay. So this already, using some other ideas, would lead to an improvement for the MIS problem. I'm not going to go into that. The other is, and the second result of the de-randomization, we have this naive way of going through the colors, this delta to the order of R. Okay, in general, we cannot get something better, but for many problems, there should be a way of, not using a full coloring and just a weaker version of coloring. I'm not going to specify that. And this, if possible, would lead to solutions for many other problems, hopefully. One particular one that I hope to be solved is defective coloring. This is the problem of coloring the graph with some number of colors such that the graph induced by each color has a small degree. Okay, so I'm writing some bounds there, d defect and delta over d many colors. So that might be another problem that might be resolved using this weaker version of de-randomization. All right, that covers what I wanted to mention. Thank you.